Okay, geometry, chapter 9, section 6, tessellations. Pause, come back and check your work from this homework quiz, or this little warm-up quiz. Quadrilaterals have 360 degrees. Octagons have 1080. Squares, interior angles are 90 degrees. Pentagons, 108. Hexagon, 120. And octagon, 135. So today we're going to use transformations to draw tessellations. Sounds poetic, doesn't it? We will identify regular and semi-regular tessellations and figures that will tessellate. Can you tessellate? Yes, you can. We will use translation symmetry, a frieze pattern, glide reflection symmetry. We will see regular tessellation and semi-regular tessellation. So we know that a pattern has a kind of symmetry if it can be translated along a vector so that the image coincides with the pre-image. We call this translation symmetry. Translate the figure on a vector so that the image coincides with the pre-image. There's a special type of pattern that has translation symmetry along a line. It's known as a frieze pattern. So both of the frieze patterns shown below have translation symmetry. So we could imagine translating, let's say, this white image on a vector down to this white image, right? Or maybe this kind of orangish image here down to this orangish down there. The pattern on the right also has glide reflection symmetry. So a pattern with glide reflection symmetry coincides with its image after a glide reflection. You could kind of imagine the reflection when you're looking at these kind of images here and how they would reflect and then glide to end up on their corresponding isometry, right? When you are given a frieze pattern, you may assume that the pattern continues forever in both directions, as though it makes up a plane. Let's identify the symmetry in each of these wallpaper border patterns. And so what type of symmetry do we see in A? Well, we certainly see translation symmetry, right? We could imagine moving along a vector and landing on an image exactly congruent to the first, right? And in part B, what do you see? Well, we see a little bit of that translation symmetry. We also see glide reflection symmetry, don't we? So we could reflect and translate combination. Identify the symmetry in these frieze patterns. And what do we see here? With these kind of turned images, we see translation symmetry. Let's see. We could translate this. Let's just take this piece, or this entire piece here, and move it over here, right? Just glide it along a vector. In this case, we could do that same thing, couldn't we? So we have translation symmetry, and also we could imagine reflection symmetry as well. Imagine a line of reflection. So a tessellation, or tiling, is a repeating pattern that completely covers a plane with no gaps or overlaps. The measures of the angles that meet at each vertex must add up to 360. So in this tessellation, each angle of the quadrilateral occurs once at each vertex, right? So we have yellow, green, blue, and red all converging at this vertex here. Because the angle measures of any quadrilateral add up to 360, any quadrilateral can be used to tessellate the plane. 4 copies of the quadrilateral meet at each vertex. See that? Every vertex has the 4 different vertices from the quadrilateral meeting. Pretty awesome tessellation. We know that the angle measures of any triangle add up to 180. This means that any triangle can be used to tessellate a plane, but we would need 6 copies of the triangle meeting at each vertex as shown, because again, the three different angles of the triangle add up to 180, so we would need to repeat that, right? We would need to have another 180 degrees to get the full 360 degrees you need meeting at the vertex in a tessellation. So, very good. So we can see angle 1, 2, 3, or angle 1, 2, 3, and angle 1, 2, 3 come together and form a vertex in a tessellated plane. Very cool. So copy the given figure and use it to create a tessellation. So we can create this by rotating a triangle 180 degrees about the midpoint of one side. So they're using what looks like a hypotenuse. They're rotating it and putting what looks like the acute angle, the most acute angle, meets up with the medium angle in this triangle, right? So we haven't formed yet an entire tessellation, right? We can translate the resulting pair of triangles to make a row of triangles. So this might be the beginning of a tessellation. We can even translate a whole row of triangles to continue the tessellation. Notice at any vertex here, look at this vertex right here. We have 1, 2, 3 different triangles in basically the top row, and 1, 2, 3 different triangles in the bottom row, all meeting at this vertex, which gives us the 360 degrees that we need, right? Let's copy the given figure and use it to create a tessellation. Once again, we can see that we can rotate the figure 180 degrees about a midpoint of a given side. There we go. And we can translate the resulting figure, pair of figures, to make a row of figures. And how about making a row of these quadrilaterals, one on top of the next, to continue the tessellation, right? Again, when we look at any of the vertices, let's look at this vertex right here. We have 1, 2, 3 triangles from this top row, and in this case we just have a 4th angle, but what do we know about that angle? We know it is a pretty big angle, isn't it? So it makes up the difference. So a regular tessellation is formed by congruent regular polygons. And you know what regular means, right? Each side is congruent, right? And each angle is congruent. A semi-regular tessellation is formed by 2 or more different regular polygons with the same number of each polygon occurring in the same order at every vertex. So a regular tessellation just has all regular polygons, right? A semi-regular has, a regular has all the same, a semi-regular has regular polygons, but 2 or more different polygons. Every vertex has 2 squares and 3 triangles in this particular tessellation. Do we see that? Square, triangle, square, triangle, triangle. Triangle, triangle. There we go. This is a regular tessellation because every figure in it is a congruent triangle. It's a regular triangle, so an equilateral triangle, right? This, of course, is a semi-regular tessellation because we have regular figures, we have equilateral triangles, and we have squares, and they are not all the same, like this regular tessellation. Can we classify these tessellations? They are either regular, semi-regular, or neither. Go ahead and pause, see what you can do, and come back. So, I don't see a regular polygon in this tessellation. It looks almost like trapezoids, doesn't it? So this is neither regular nor semi-regular. In figure 2, it looks like they're all congruent, right? They're all regular triangles, so this is a regular tessellation. And in this figure 3, we have some different shapes. Do we see squares? We see some equilateral triangles, and even we have some hexagons, regular hexagons. So we do have regular polygons, and they're not all the same polygon, so this is a semi-regular tessellation. So determine whether the given regular polygon can be used to form a tessellation. If so, draw the tessellation. Can the triangle here be used to form a tessellation? Yes. And it's similar to the one we just saw on the previous page, right? Remember, 6 equilateral triangles can meet, converge all at a vertex. 6 times 60 degrees equals 360. And we have what is a pentagon here, right? Looks like it's regular and a equilateral triangle. So each angle of the pentagon measures 108, and the equation 108n plus 60m equals 360 has no solutions, with n and m as positive integers. So we cannot form 360 degrees at any given vertex with a combination of these pentagons and equilateral triangles. So there is no tessellation. This was just a decoy up here. There's no tessellation we can make. Let's try it again. Can we form a tessellation with this polygon? If so, draw it. And once again, we have a hexagon. Yes, we can form a tessellation. 3 equal hexagons meet at each vertex, right? And those add up to 360, those 3 angles. And a square and the hexagon. Can that work? Let's see. No. And once again, you can think about the fact that the square has a 90 degrees at each angle, and our hexagon has, what, 120? So is there any combination of 120 and 90-degree angles that can give us the 360? Okay, so hopefully this helps as you give this assignment a try. Have fun.